right, so we're going to look at a practice problem designated in this picture. We have Doug is going to push this crate up this ramp. The crate is at 20 degrees with respect to the horizontal. The ramp is at 20 degrees with respect to the horizontal. It's 2 meters high. The crate's 5 kilograms mass, and Doug is pushing purely horizontally with a force of 25 newtons. Now, we also know that on the ramp we have a coefficient of kinetic friction, which is equal to 0.015. So our question is, what is the total work being done on the ramp, and how fast is the crate going at the top of the ramp if Doug starts it from rest, just overcoming static friction, and goes all the way to the top of the ramp. All right, so the first idea is, well, what's the net work? If we're going to look at net work, we need to do a free body diagram, because work, of course, is our force times our displacement times the angle between them. So let's draw a free body diagram of the crate. All right, so what forces are acting on the crate? What are those interactions? Well, we know we have the force of gravity. So the force of gravity acts down, straight down, Earth relative. We have the normal force acting on the crate. That's perpendicular to the surface. So here is our normal force perpendicular to that surface. We have the force of friction, and the crate's being moved up the ramp, so that force of friction is going to be down the ramp. There's our force of friction. And we have Doug pushing on the ramp, and he's pushing purely Earth horizontal with 25 newtons. So there's our free body diagram. Now we also have to recognize what is the direction of the displacement, because we're going to look at the angle between the force and the displacement. So the displacement is up the ramp at that angle. So here is our displacement direction. Now, I put that away from the free body diagram. We don't want to think it's a force, so we don't put that on the free body diagram. We want to keep it away from that free body diagram. It's going to help us remember the direction of that displacement. Okay, so I have 4 forces that I am going to look at the work being done to find the net work. So let's start with force number 1. The work done by force number 1, well, that's going to be equal to the force number 1 times the displacement times the cosine of the angle between them. So we know force number 1 is our force of gravity. What about the displacement? Well, that's the displacement up the ramp. So we need to know what this distance is. Now I'm given an angle and I'm given a height, so we can use our trigonometry to get that displacement. Our height is opposite, so we know that the sine of 20 is opposite to over our displacement. So our displacement is going to be 2 divided by the sine of 20 degrees. So we'll calculate that. 2 divided by the sine of 20. And we get a displacement equal to 5.85 meters. So this D is equal to 5.85 meters. All right, so our displacement of 5.85 times the cosine of the angle between the two. So the angle between our displacement and the force of gravity. So if this is our displacement, we have 90 degrees plus the additional 20 of the slope. So that's going to be a cosine of 110 degrees. So that's our work done by the force of gravity. So that is going to equal our force of gravity. Well, that's 5 times 9.8 times our displacement, 5.85, times the cosine of 110. So negative 98 joules. Now, should it be negative? Well, the displacement's up the ramp and gravity's working against that. So yeah, our work should be negative. All right, next force. The work being done by Doug. Well, that's going to be the force of Doug times the displacement times the cosine of the angle between Doug and the displacement. So our force of Doug, well, we're told he pushes at 25 newtons. Our displacement, again, 5.85. And the cosine of the angle. Well, if this is our displacement, we kind of visually move that down where we can compare it to the force Doug is exerting. That's 20 degrees. So the cosine of 20 degrees. So 25 times 5.85 times the cosine of 20 degrees, we get 137.4 joules. It's positive. Should it be positive? Yeah, Doug's helping that crate go up the ramp in the direction of the displacement. Perfect. Force number 3. Let's look at work 3. That's the normal force times the displacement times the cosine of the angle between the displacement and the normal force. We don't know the normal force. The displacement's 5.85, but what do we immediately see about this cosine? It's 90 degrees. So the normal force is acting perpendicular to the displacement, and therefore no work is done by the normal force. And our last force, well, that's the work being done by the frictional force times our displacement times the cosine of the angle, of course, between the displacement and the frictional force. So our frictional force, we're not given that. We're given the coefficient. We're not given the frictional force. We're going to come back to that. Our displacement, 5.85, times the cosine, well, our displacement is 180 degrees from the coefficient, or excuse me, from the frictional force. So in order for us to get this value, we need to determine the frictional force. We want to remember that friction is equal to mu times N, our kinetic frictional force. Well, that means in order for me to determine the frictional force, I have to figure out N. All right, well, let's look at N from the analysis of forces. I'm going to erase up here. Okay, small little pause in the video, if hopefully that connected well, and now I don't have my black marker, but we'll use blue and red. Okay, so if I'm going to look at my horizontal and vertical forces acting, we're going to do a force analysis to determine the normal force. Now, I'm on a ramp, so I need to rotate my coordinate system. Because if I do that, I see that the normal force is only acting in the vertical dimension. And so the ramp is not moving, or sorry, the crate is not accelerating in the vertical dimension on a rotated axis. So I probably can get the normal force. So let's look just from that vertical direction. So we're going to start here recognizing that the sum of the forces vertical are going to be 0. Okay, so we have force number 1. Well, that has a component that's horizontal. It's going to be Fg times the sine of my 20 degrees. It will be in the negative prime direction, and vertically it's minus Fg cosine of 20 degrees. Force number 2, that's the force that Doug's exerting. He has a horizontal component in the rotated coordinate system, 25. And if I think about how it rotated this direction, it's the cosine of 20 degrees. And in the vertical direction, we have 25 times the sine of 20 degrees. But in that rotated vertical dimension, the component for Doug is in the negative direction. So we want to be explicit about that negative. Force number 3, that's our normal force. Nothing horizontally. It is positive in the vertical dimension. And force number 4, well, that's purely horizontal. Okay, so we said we're going to look at the vertical dimension, summing those forces to get them equal to 0. So we have minus the force of gravity times the cosine of 20 minus 25 times the sine of 20 plus the normal force is equal to 0. So that means my normal force is equal to the force of gravity times the cosine of 20 plus 25 times the sine of 20. And so if we figure out what that equates to, we have 5 times 9.8 times the cosine of 20 plus 25 times the sine of 20. And we find that our normal force is 54.6 newtons. All right, well, if the normal force is 54.6 newtons, then my force of friction is 0. Okay, so we have our normal force of 54.6 newtons. So that means our force of kinetic friction is 0.015 times 54.6. And that is 0.82 newtons. So we're going to put that up here in our work relationship. And we have 0.82 times 5.85 times the cosine of 180, which we know is -1, times 5.85. We get negative 4.79 joules. And again, negative, friction is opposing the direction of the displacement, and so it's going to provide us with negative work. And so we see here then that our net work, part 1 of our problem, is -98 plus 137.4 minus 4.79 joules, 34.61 joules. So that is our total work being done on the crate. All right, so how fast is it moving at the top of the ramp? Well, we could do a whole force analysis and a kinematics process and all of that, or we can recognize the power of work and energy. If we know that the net work on an object, if we know the net work, we want to remember the work energy theorem, which tells us that the net work is equal to the change in kinetic energy. Well, the change in kinetic energy is the final energy minus the initial kinetic energy. And we're told that this crate starts from rest, so our initial kinetic energy, of course, is 0. So our net work is just equal to the final kinetic energy. And the final kinetic energy is related to the speed, and so I know exactly how fast the crate is going to be at the top of the ramp. Okay, we keep having technical difficulties, so hopefully this is going smooth. So our work net is equal to our final kinetic energy. So our work net is 34.61 joules. That's going to equal 1/2 our mass of 5 kilograms V final squared. So we're going to solve for V final, and so 34.67 times 2 divided by 5, and take the square root of that, and we have V final, the speed at the top of the ramp, is equal to 3.72 meters per second. So again, we could have done all that kinematics and all that force analysis, but work energy is a heck of a lot easier when determining some properties of an object's motion. All right, good job. All right, so we're going to look at a practice problem designated in this picture. We have Doug is going to push this crate up this ramp. The crate is at 20 degrees with respect to the the ramp is at 20 degrees with respect to the horizontal. It's 2 meters high. The crate's 5 kilograms.